Hopefully you've tried this question and you've worked through it. I'm going to try and work through my examples here and see what I can come up with. 3 to the negative x I know can be written as a 1/3 to the positive x, which represents exponential decay. And I'm going to see which ones of these might equal that. So 27 is the same thing as 3 cubed, and then we have a 1/3 to the x plus 3. From here, I could write that as there's a couple different ways I could write that. I could take that 1/3 and make it to the -1, and then I can compare it to 3 to the negative x, or I could take this 3 to the 3 and write it as 1/3 to the -1 to the 3, which would make that a -3. So either way we can do that. I'm going to work with what I've got here. I don't like working with fractions if I don't have to, so I'm just going to compare these to 3 to the negative x and see what I get there. Bases are the same, we're multiplying. I'm going to actually do the power of a power rule here first. I'm going to get 3 to the negative x, that's supposed to be a multiplication there, and then minus 3 when I put that negative through, and a 3 take away 3 would be 0, so that equals 3 to the negative x. Okay, for the next one here, I've got 9 being the same as 3 squared, and that's times 3 to the negative, and then I'm going to put that negative through the bracket, negative x take away 2. Add those exponents, 2 take away x take away 2 would be 3 to the negative x again. So it's the same as well. 9 over 27, both of those can reduce. 9 can go into itself once, and 9 goes into 27 3 times. And that's to the x, which is what I had rearranged the very first one as, which could also be written as 3 to the negative x. So all of those are equivalent so far. Now 27 I know is the same thing as 3 cubed, and that's to the negative x over 3. I'm going to do power of a power where I'm multiplying those exponents together. I have 3 times negative x over 3. The 3 times and the divide by 3 cancel out. That gives me 3 to the negative x, also the same. Now, 1 over 9, that would be 1 over 3 squared, or I can take that and make that 9 to the negative 1. So I'll do that first. And so that's going to give me 9 to the negative x over 2. 9 is the same thing as 3 squared, but then that 2, the squared, is going to multiply the negative x over 2, and that's going to leave me with a 3 to the negative x, also the same. All right, 81, that's the same thing as 3 to the 4, so that's 1 over 3 to the 4, which I can slide that up to the top. I'm just doing that one in the reverse of what I did with the 1/9. 1/9 I changed that up to a -1 first and then changed it to a 3 squared. I'm just doing it the backwards way this time. Doesn't really matter which way it goes. This way what I've got is 1/3. That's all to the 4. I haven't moved that base of 3 up to the top. All I've done is said if I have 1 over 3 to the 4, that's the same thing as 1/3 all to the exponent of 4, because 1 to the 4 is just the 1, and then 3 to the 4 is the 81. The reason I did that is so my bases are the same. And the rule is when the bases are the same, I can just add my exponents together. So 1/3 is my base. I'm going to have 4 plus -2, or 4 take away 2 with an x. Now that is not the same as the first one, so that's one that is different. All right, and this last one with a negative base like this, it is not actually an exponential function because your base has to be between 0 and 1 or greater than 1. It can't equal 1 and it can't equal a negative number. So this is not the same either. So these ones are all the same. Okay, we're moving into some scenarios and coming up with our exponential equation. For each of the following scenarios, determine an equation to represent the value. So if you think of your generic equation, we have y equals a b to the x. So a is your initial value. So if I look at this question, a fine piece of jewelry increases exponentially in a value at a rate of this much. So there's my percent increase. So it's increasing in value. So I'm adding, increasing. 0.25 in decimal form would be 0.0 move that decimal 2 places, 0025. If it's currently worth $500, that's our initial value right there. Write an equation to represent its value in dollars n years from now. So V for value would equal the initial value, 500, and then the B value is always 1, so B is equal to the 100% plus, in this case because we're increasing, by 0.0025, or that B value would be 1.0025. So that's what's going to go in our bracket here, 1.0025, and then that's going to be to the exponent n for n years from now. Try the next couple, actually the next 3, see how you do, and then we'll take them up. All right, a car is purchased for $32,000, so that's the initial value, that's the A, $32,000. And it's decreasing, so we're going to subtract at a rate of 12%. So 12%, just take 12 divided by 100, 0.12. Our B value then is 1, take away 0.12. So B should equal 0.88. So that's our exponential decay there. And that would be to the exponent of n. All right, bacterium doubles every hour. If there's only one bacterium initially, write an equation to represent the population, so P for population, H hours from now. So it's doubling every hour. So think of doubling every hour. You've got your 100% plus you're adding another 100%. That's going to make your base be 2. So you can put your 1 here for your initial value, 2 to the h. Or you could just write that as 2 to the exponent h for your population. Okay, radioactive substance has a half-life of 123 years. So that means it takes 123 years for it to cut in half. So our initial, or our B value, we start with 100%, but then we're decreasing by 50%, cutting it in half. And then that leaves us with a B value of 0.5, or you could just use the fraction 1/2. So the number of grams remaining is capital G, and this one's kind of, yeah, the half-life is 123 years, so we'll talk about that. Initially there's 100 grams, and then we're going to have our 0.5 here. If I had this mass sitting around for 123 years, it's going to actually cut itself exactly in half and be equal to 50. And then for another 123 years after that, it would be down to 25. So really we're taking our n, our number of years, and we're going to divide it by 123 to see how many times it's actually going to cut in half. So half-lives and doubling times, the exponents can be kind of tricky because you've got to take n, if n is your number of years, and divide it by either how long it takes to cut in half or how long it takes something to double. Up here on the part C, it was just doubling every hour. You could have had that exponent h being divided by 1, but h divided by 1 really is just h. Okay, hopefully that makes sense.